Thank you all for being here. This is really great. Really excited. It's kind of a new sort of kickoff to the Global Health Global Series seminar. So we're excited to be here. My name is Johnny Olden. I am the Assistant Director for the Triangle Center of Evolutionary Medicine, coined TRICEM. We are housed in evolutionary anthropology, but what's really unique about us is that we're comprised of multiple institutions. So yes, we are at Duke, but we also are equally parts of NC State and UNC. So if you're interested in what we do and what more of this program is like, please check out our website, email me, Johnny Olden. I think our info is on the main webinar info page, and also Charlie Young, who's a director. But TRICEM is an incubator of evolutionary medicine, and we really pride ourselves on connecting people and ideas and organizations throughout really the state of North Carolina. We're kind of extending out pretty far to other institutions and universities. So today's program is meant to be fun, but also highlight the importance of pandemic and pandemic prevention. And as such, TRICEM was awarded a PIP Phase 1. And PIP is an acronym for Predictive Intelligence for Pandemic Prevention. For PIP Phase 1. And we're about halfway through. It's a 1 year, $1 million grant. And we've really connected to a lot of really amazing groups and people across the Triangle. And there's been a lot of momentum and ideas going forward. And we're excited to announce that we're going to be applying for a Phase 2 Center grant, which is this big $18 million 7-year grant. We're really excited. Deadline's fast, though. It was just announced last month. Deadline's in 2 months already. But if you're interested and want to collaborate with some ideas, please reach out. We're always happy to more. Again, reach out to me or Charlie. Okay. And as part of our PIP Phase 1 grant, we have the pleasure of working with wonderful student RAs, one of which is Rachel Keener over here, which you can't see on camera. She has been fantastic and gone above and beyond to help organize this series, but also a number of other pitfall programming sessions that we've been doing. So be on the lookout for some more invitations on that. Okay, I've been talking about now we're gonna get to the fun part, the whole debate style. So it is my pleasure, and I'm excited to introduce 3 expert panelists who will make their case for what unexpected pathogen they think will be the next pandemic. Hopefully not, hopefully we learn. So we're excited to introduce Dr. Christopher Woods, who is the Executive Director of the Hubert Jurgen Center for Global Health, Professor of Global Health, and the Chief of Infectious Disease Division at Durham VA Medical Center. Dr. Asiya Gusa, the Assistant Professor in Molecular Genetics and Microbiology, and Dr. Thuy Le, who is the Associate Professor of Medicine, Molecular Genetics and Microbiology, and is also a Duke Global Health affiliate. So real quick, before we start the structure of the talk, we're going to have about 5 to 7 minutes per speaker. And then we're going to ask to refrain from any questions until the end of all 3 of them speaking, which will have a Q&A slide up if you want to submit anonymously or via chat, any of that in person. We welcome any and all. And then after that, we're going to have a 2-minute per person closing remarks, and then we'll vote. And the vote also will be via QR code anonymous. Okay, thank you. Please look open questions until we are done. Yep.
All right. We're off and running. I will try to be quick. It's wonderful to be here. Thanks to Charlie and the whole group for getting this together. It's always fun. It's nice to see a full room here at in 040. So emerging infections, pandemic potential, etc. I've been working in the area a long time, 2.5 decades or so, and I worked with many in the room here as well. I honestly spent most of my time talking about things that I wasn't sure was going to happen in the large scale that we experienced with COVID, but COVID certainly changed the type of discussion we are having today, given the great reality of what a true pandemic looks like. Drivers, we need to take into consider when we think about what the next pathogens are, what are the driving the factors that are likely to make a new pathogen to emerge or an existing pathogen change how its epidemiology is affecting us. And those most prominently include globalization, the movement, and that facilitates whatever it is getting around the globe. And then we think about anthropogenic land use change. I think that's a huge thing when we talk about new pathogens emerging, particularly how we are affecting our forests and how we are performing mass agriculture. And this is going to be relevant to the my suggested family of viruses that is that I'm going to try to defend as the one of the leading, if not the most important virus or a pandemic potential virus coming up. Viruses in general are widely considered the most likely cause of pandemics. There's many reasons for that, and just the sheer number of them, but also the variety we see in animals and humans. And a lot of this, we expect that this will be a zoonotic transmission event that'll take place, something going from either domestic animals or wild animals into the human population and spreading from there, much as we saw with COVID. We talk about influenza. I was not allowed to present influenza despite its great likelihood. We talk about coronavirus. I slipped that in, but I can't pretend it. Coronaviruses, and there is a high likelihood we'll see ongoing COVID issues and other potential problems. We hear about things like Rift Valley fever, Bunya viruses, filoviruses. Everyone gets very excited. I think Charlie really wanted me to defend Ebola virus and Marburg viruses as the next most likely cause. And I did not go forward with that because to some degree we've already had it, although that was really an interesting event and had we could spend a lot of time talking about it. But I am here to defend paramyxoviruses, and I'm doing this at the family level. And paramyxoviruses, these are RNA viruses, and most of the time when we're talking about pandemic potential, we're talking about RNA viruses. There's a number of reasons for that I won't go into, but the paramyxoviruses are widely spread among mammalian groups. There are 4 major genera in the family that we think about. Morbillivirus, which is really interesting because the classical animal pathogen was rinderpest. Rinderpest is really interesting because it was one that was recently, or in 2011, actually eradicated. The only other eradicated pathogen being smallpox, and it is somewhat of a precursor for the measles virus, which we're very familiar, which is also a morbillivirus. Uniquely has the highest R0 amongst amongst viruses and really known pathogens, higher than with an R0 of 30 for those of you who kind of follow those things. There are Rubella which is the mumps viruses, which has other similar viruses amongst the animal kingdom. You have Respirovirus, as you may have heard of, parainfluenza virus. This is an example there. And then you have what I'm going to present as being the most concerning, which are the Henipaviruses viruses. And the Henipaviruses viruses are the youngest of the genera in the paramyxoviruses, being first identified in the mid-1990s. 2 major viruses that we think about in the Henipaviruses. One is the Hendra virus. Hendra virus is a great story of horses, from bat to horse to people. Does not have demonstrated person-to-person or transmission, so no ability to maintain a infection in that regard. Our colleague at Duke NUS, Wen-Fa Wang, was incredibly important in identifying that virus and developing some of the vaccine that was ultimately came out to help be a countermeasure for that. So I'm getting time notification. So that's Hendra virus was the first of those. Then you may not have heard of Nipah virus. Nipah virus, I've got up here as my the different outbreaks that occurred. It came right on the heels of Hendra virus. Really interesting example of a One Health classic pandemic situation where you have deforestation situations. The original outbreak was in Malaysia. They brought in planted mangoes near piggeries, fruit bats hanging out eating the mangoes, peeing and pooping and doing everything into the piggeries. Large outbreak of disease among the pigs, spreading amongst the pigs, dying and needed to be culled. 285 individuals, humans, got encephalitis, and there were over 100 deaths. This is in 1998. Subsequent expansion, and this is important when we think about pandemic potential, getting into India, Bangladesh, and then subsequently the Philippines, and each time slightly different epidemiology taking place. And actually seeing here, you're starting to have person-to-person transmission. Again, this is needed to sustain an outbreak. Now, the R0 for Nipah virus is less than 1. Important. Why? Because then you can't sustain a pandemic. So you don't have, with the current Nipah viruses, the ability to sustain and expand an epidemic, but we are seeing some elements pop up. Now, above and beyond that, there are, when you start doing your virus searches, which are taking place and happening around the globe, and we're looking at various animal groups, we look at rodents, we look at bats, we look at non-human primates. Those are the entities that are likely to house the viruses that are going to be transmitted to us. They found in the, I think it was a 2012 study, 66 more previously unidentified paravixoviruses that had not been previously identified, only looking at about 10% of the species of bats. They have identified relatives of the Hendra virus in Cameroon and a subset of folks, but that interestingly does not cause human disease at this point in time. So we're seeing the spread geographically continue. We see variation in these viruses. The potential for severe diseases there. There are not the countermeasures extent to actually fight these. So there's no proven vaccine yet, although there are candidates. There are no proven therapies, although they do have some monoclonal antibodies in development, and there are no drug therapeutics that have been approved. So another important consideration when we think about pandemic potential. And I think I've used probably more. So I'm going to stop there. Okay.
Scary.
Hey everyone, hello. My name is Asia Gusa, and I'm going to introduce you to, you're probably more familiar with bacterial and viral threats, but I'm going to introduce you to a new threat on the scene, which we're already beginning to see evidence for, emerging pandemics of fungi, okay? So this has actually been recently in the media and press, and sometimes it takes that for popular culture to sort of mix science fiction with real science, what's actually going on. The HBO series, The Last of Us, is sort of an introduction of this pathogenic fungus that adapts thermally into the environment and then is able to infect humans and ends up causing a zombie apocalypse. And we think that that's likely. No, but I do want you to know that this is actually based in real science. And it's something that I study in my lab is heat stress and thermal adaptation in a pathogenic fungus. So I'm going to talk to you about fungi, the whole kingdom potentially as the new potential pathogen that could cause the next pandemic. And in fact, if you're not aware, we're already in the midst of a pandemic of Candida auris, which is a fungal pathogen that's spread in healthcare environments. So I'm going to start by, if you look on to your left, there's over 20,000 species of fungi that currently cause disease in plants. They're in fact a major blight of crops like corn, wheat, tomatoes, bananas, everything. And they actually threaten our whole food ecosystem. So the question is, if they're causing all these diseases in plants, why are there only a few, relatively few fungal species that actually cause disease in humans and mammals? And so the one that I study is Cryptococcus. That's one of them. It's actually the most lethal fungal pathogen. It kills over 100,000 people every year, but it's primarily associated with folks that have HIV/AIDS. But why are there so few fungal species that cause disease in humans? And a big part of this is sort of the science fiction behind The Last of Us, but it's that our core mammalian temperatures actually act as a thermal barrier. So the vast majority of fungi, and particularly those that are found in the environment, cannot survive at our core body temperatures of 98.6 degrees or 37 degrees Celsius. In fact, in recent studies, we found that only those fungi that can survive at that human body temperature are actually capable of causing disease. So what does this mean as far as what's happening in our environment currently? Well, currently we're seeing record-breaking temperatures, heat stress, in particular due to high temperatures, but also we're seeing a lot of climate disruption. So these fungi in the environment are natural decomposers. All right, they're expert decomposers in the soils, and we rely on them actually for a lot of the products that they produce. But they're very adaptive because of that. For the most part, though, the temperatures in the soils are fairly endothermic, and so we don't see them as being a major threat. However, they're going to be experiencing heat stress on a continual basis that will cause those fungi to have to adapt to growth at higher temperatures. In doing so, that could increase their pathogenic potential. And so we're already seeing, the other thing I wanted to mention though, is that there's the disruption in the climate, such as floods, drought, hurricanes, tornadoes. It's actually dispersing fungal spores in the air and in the soils to locations where they haven't been found previously. So we're already seeing the geographic spread, and you may have heard in the news recently about valley fever, which is coccidioides, spreading from where it was relegated primarily to the southwest of the United States. It's spread to nearly all 50 states now, and we know that climate change is causing that to happen. So we've seen both an increase in cases and also a geographic spread of fungal diseases. So just recently in 2022, the World Health Organization just released its first ever list of health-threatening fungi. So you may have recognized some of those above, including Candida auris, which I'll speak a little bit more specifically. Recently, also, Candida auris in 2019 was identified by the Centers for Disease Control and Prevention as an urgent threat. And this is because not only has it emerged and simultaneously around the planet in at least 4 different kind of clonal spreads, but it's also highly drug resistant. So we're not only seeing the emergence of fungi causing disease at case levels that we've never seen before, we're also seeing that they're multi-drug resistant. In fact, Candida auris is, some clones of Candida auris that we found in patients are resistant to all 3 major antifungal classes of drugs. So fungal diseases are on the rise, and they can cause invasive diseases with very high mortality rates. Right now, we have about 1.5 million deaths due to invasive fungal diseases every year worldwide. They have a high mortality in part because they're actually eukaryotic pathogens. So their cells actually resemble our cells. So our access to types of drugs, and also there's no vaccine, that our drug targets are fairly limited. There's also not been a ton of research and development been focused on treating fungal diseases because they primarily infect immunosuppressed or immunocompromised people. Okay. Fungal diseases can be transmitted through spores in the air, like the one that I study, but also they can be transmitted person to person. So I just want to speak a little bit more about drug-resistant Candida auris. So what's really unique about it is that it emerged on multiple continents within just a few years. This is really just within the last decade or so. And I want to correct my slide. There are about 10,000 cases that we've documented worldwide so far, but in the US, we have seen that number triple in just the last 2 years. So it's typically spread person to person in healthcare facilities. So you may go in with one infection and come out with Candida auris, potentially causing mortality. They're extremely drug resistant, and they kill 2/3 of the people infected if it goes invasive from the skin to the bloodstream. And so one of the proposals is that this has emerged due to climate change, because again, how do you get sort of the simultaneous evolution on multiple different continents? And you can see over the years, the geographic spread. We've also recently found environmental reservoirs. So places in the environment where we can isolate, we can extract this particular Candida auris species. And we haven't directly made the link yet that it's been thermally adapted and that's what's causing it. But certainly we're starting to see not only Candida auris, but we're starting to see another group of ringworm infections. You might start to hear about them in the media. They're emerging on multiple continents. Ones that species that we've never seen before that are also multi-drug resistant. And part of that is in the environment, we're using a lot more fungicides in the environment on our crops and whatnot, and we think that might be feeding into. We're also using corticosteroids, and that could be feeding into this drug resistance that we're seeing in emerging fungal pathogens. So just to sort of conclude my intro, we don't know exactly what the impact of climate change is on environmental fungi. We can just see that there are emerging pandemics now of fungi that we've never seen before. So whether or not if the link is climate change, the actual result is what we're seeing. And so those fungi in the environment are encountering new stresses that they have not experienced before. They're moving to foreign lands. And so that may result in mutations and adaptation. In my lab, we study mutation rate, and we actually see that there's a link between heat stress and increased mutation rate in fungi. So it's very possible that we're actually stimulating mutational events to occur with these extreme stress events. So hopefully not The Last of Us, but there are going to be adaptive changes that occur that we need to really be focused on. And unfortunately, our surveillance of fungal diseases is very poor. We have very few diagnostic tools, so we were largely underreporting the number of fungal diseases that are currently abundant. Not stop there.
Well, great. This is supposed to be fun. Well, I don't know why I said yes to this. If I know Chris is doing this, there's no way. And then Lisa is like taking my field. I'm a mycologist, so like I have no more pathogens. But hang tight. I'm a fighter, so I'm gonna fight. So listen, so I wanted to first, when I was asked to give this talk, I was thinking that the only way for me to predict the future is actually see what happened in the past. So if you look at what happened in the past, these are global pandemic in the past. The first one is the Black Death that killed half of the European populations in the 1400s. And then you got smallpox that went throughout basically many centuries, but it killed 200 million people. And that's what we thankfully eradicated. Cholera killed 1.5 million people. But those pandemics happen within 600 years span. And then with the next cluster, within 100 years, the last century, you got 4 major pandemics, starting with your famous Spanish flu in the 1918, ended with the HIV pandemic. Each killed 150 million people, and HIV killed 40 million people. These happened within the span of 100 years, like I said, and within my lifetime as a physician, we've seen, just over the last 20 years as a physician, we've seen 7 pandemics. And so started with swine flu, H5N1, and then SARS, influenza, H1N1. Luckily, that wasn't very lethal. Then we got MERS, COVID, Ebola, Zika, and COVID-19. So 7 within 20 years of our 21st century. So I hope I convince you that the risk for pandemics are increasing. So the question is why? And Chris had talked about this, the major drivers are important, understanding the major driver. Deforestation, we chop down trees and we make space for ourselves. And there's increasingly humans and animals come into closer contacts, and certainly will share the environment. And there's a lot of pathogen jump species, as you already know. In fact, 60% of infectious disease have a zoonotic origin, and 75% of emerging infectious diseases have a zoonotic origin. So clearly, there's a huge issue of that. And then there's global warming that Elisa have already talked about that reduce the interspecies thermal barrier that allow tropical infectious disease to postulate, as well as fungal pathogen. We talked about that. You got population densities and urbanization. People live close together, therefore disease spread rapidly. It's very difficult to eradicate, very difficult to track as well, particularly with infection that we've gotten, like COVID-19, would transmit very readily, but doesn't cause symptoms. So you don't even know that you're infected. So these are issues. And then human migration, obviously, is an issue that brought outbreaks and epidemic from pandemics, right? So these are the major drivers. And when you think about the pathogen that can have pandemic potential, you think about 3 things. First, they have to have ability to mutate rapidly. and adapt to the environment, adapt to its new host. And so antigenic drift and antigenic shift, as you know very well from influenza, this is why we got to have new influenza vaccine every year because of different strains and antigenic drift that happen in H1N1 and H3N1 circulating influenza every year. And then once in a while, you got this shift where you got multiple species. For example, your virus living in the pig will mix with the virus in humans and then mix with virus from bird. That's how you start having new viruses and you have no immunity for, right? Number two is the ability to transmit between species and transmit between humans. That's really important. And the third one is the ability to really impact public health, economics, politics, and as you already know. So the way that I approach this, having said that, obviously there are probability of certain pathogens that do that, as we just talked about. And what I'm going to do is instead, I'm going to violate your request of sticking with one pathogen. What I'm going to do is to actually argue for classes of pathogen, but believe me, I'm not going to follow your suit. So argue for classes of pathogen, and then at the end, I'm gonna vote for one. I'm gonna put up one for your vote. But first of all, RNA viruses that Chris already talked about, and of the 12 RNA viruses that cause human disease, 7 of them or 6 of them already cause pandemic. So clearly, influenza, coronavirus, Ebola, Zika, HIV already cause pandemic. The others certainly have caused outbreaks and epidemics that haven't gotten to the point of pandemics, and because it's lacked that sort of transmissibility and R node not being very high, etc., that Chris had talked about. So there's a huge potential. They are very successful pathogen, and there's about 200 RNA viruses circulating in human, or not circulating, but actually infected human, and there's a lot more in animal. And as we come close to them, germ species, what we call epidemic or spark risk going to happen. The issue spark risk going to happen. But the reason I'm not going to argue for RNA viruses or pick one out of that whole class like Chris did is because I think we learn a lot from COVID. And I think that we know how to reduce the spark risk. I know we know how to reduce the transmission or the spread risk. And we have vaccine that we've, never had such a fantastic vaccine and fast way to do it, very effective way to do that. I think there's features of pandemic that we can control. So I'm not going to argue for that. It's not challenging enough for me. The next class, the pathogen, obviously fungal pathogen that Elisa talked about. And of those, Candida auris, and I would argue Cryptococcus, as you know, Cryptococcus gattii went from a tropical area to British Columbia, right? Islands that we had all these outbreaks. And then the endemic mycosis, Histococci, Telomyces, Emojimyces are endemic mycosis that can infect both immunocompromised, but also immunocompetent people. And certainly you got others. I wanted to talk about one particularly interesting one. I can't even know how to pronounce it. I want to call it BD. Batrachochiticum dendrobatitis. I challenge you. I don't know what it is about mycologists. They really have a lot of time in their hands. Trying to come up with these names. But anyway, BD is the pathogen that has essentially eliminate 90 species of animal, 90, and another 500 at risk. And they really, really eliminate, eradicate amphibians and frogs. Right, in population, so they can do that. The reason is because these amphibians have cold-blooded, they're cold-blooded mammals, so they don't have this species barrier, and fungal can infect them. So with global warming, like Elisa said, they're going to bring fungal pathogens. There are about 1 million fungal pathogens. 5 million of fungal pathogen as opposed to 200 viruses, RNA viruses. So there's a lot more potential when the earth warm up, your species barrier reduce, is gonna really attack. The only thing that keep it really from them is our immune system. We have a very intact immune system, and that's our strength. But if, God forbid, the fungus start talking with HIV and try to exchange genetic material and learn how to attack the immune system, we're gonna be in trouble with the fungus and not virus, because they're everywhere. You don't really need human to human transmission. But I'm not here to argue for fungus. And the reason is I think that our immune system had evolved through generation, and it's not something that can be easily infected. So I'm talking about all the drivers, temperatures, and all of that. I don't have time to go through these, but I'm not arguing for fungal pathogen. What I'm arguing for is unexpected. The silent pandemic of AMR superbacteria. Right. And so I think, these are, just last week I was on clinical service and I had 2 patients whom I run out of drug to treat them. This is scary. And this has happened as we speak. So we got methicillin resistant Staphylococcus aureus. We use vancomycin for that. Guess what? The bug developed vancomycin enterococcus, resistant enterococcus, and then gram negative, gut. It basically learned how to really, completely dysfunctional penicillins and beta-lactam antibiotic, which is a huge class of antibiotic that we use. And so by producing beta-lactamase, it hydrolyzed the beta-lactam ring and completely make it non-functional. So that is becoming a huge issue now at Duke here as well, and all over the world, particularly in low middle income country where antibiotics are not being regulated and can be given to anybody without prescription. Then you've got carbapenem, which is a drug, the biggest gun antibiotic that we have, and now we have carbapenem resistant bacteria. So this is exactly what I deal with on the ward just last week. I had carbapenem resistant bacteria. And then you got tuberculosis, multi-drug resistant, extended drug resistant tuberculosis spreading in human. And we are only beginning to see how to have some other drug for this. And then you got obviously multi-drug resistant fungal pathogen emerging. So I think these are pandemics that happen right now and at a very rapid speed. I'm going to skip this slide and go back to this. The rate of antibiotic approval has decreased dramatically while antibiotic resistance is going up. So there's multiple drivers that you think we're going to go back very soon if we don't do something about this to the pre-antibiotic era, and which is very scary. What that means for you and I is that we no longer, you can get lethal infection that is multi-drug resistant by having a cut. Like before penicillin become available, people die from a sore throat. So this is, we're not talking about, so we won't be able to do modern medicine the way that we used to do now. We can't do surgery on people. We can't do bone marrow transplant. We can't do any intervention that we're able to do in modern medicine. If you run out of tool to treat these bacteria has been around for a long time. So how do they postulate back? When you think about antimicrobial resistance, it's not just human overuse it. Actually, 2/3 of antibiotic use are in the agriculture sector, in animal feed. So when penicillin became available in 1940, we give it to animal as well. And veterinarians figure very quickly that it makes them healthy. But in addition, there's a side effect of making them fat. They're like, wow, they grow actually 100% faster than without penicillin, with antibiotic. So they use it and put it in food to stimulate growth. And this is an industry that's been going on for 60 years. And 2/3 of antibiotic production in the world are being used in animal production. And the feces from the animal go into the environment. Their food now contain antimicrobial resistant pathogen Salmonella. Their manure go into the environment, go into the plant, go back to human. I think this is a very complex issue. And it's not just you and I overuse antibiotic or overtake antibiotic. It is environment. This is a global pandemic happened in front of our eyes without us even being aware of it. Death from drug-resistant infection is set to skyrocket to 10 million and bypass cancer, diabetes by 2050. And this is no joke. When you see that 10 million people die from antimicrobial resistance. My last slide.
Okay.
So I think for you as young master students and young generation, there's a lot to do here, not just pandemic preparedness, obviously you can, but there's something you can do right now as a master student and a master graduate. You can be involved in all of these areas to trying to reduce antimicrobial resistance in policy to get the agricultures and the human health sector to work with each other and collaborate. This is a huge challenge and will take the entire village, each of us, to work on it. Thank you very much for your attention.
Thank you. Right.
So I can go ahead and share your screen.
I think I just did it here.
No, I have to stop mine, and then you should be good to go. Yeah,
There we go.
there
Okay. All right, so here's the fun part, more of the fun. Thank you all, that was really great. Now, we'll take questions from anyone in the audience. And for people in Zoom and or in person, you can also submit via the QR code. Or you can send a text or visit the website to submit anything you want anonymously. Answers will populate kind of like a word cloud. If you choose to use it, go for it. Not, it's okay. It's kind of a fun way to see questions, but also we want to, encourage a dialogue that's fun. And you have three amazing experts here. Let's use them. So with that, we'll be taking questions, fielding them on the chat. So we have a couple coming in already in the Q&A and the chat. So we'll field that. But does anybody have any questions within the audience? We'll start with you guys first. Any of the global health students, that's a good opportunity to step up, ask some questions. Yes.
Hi. Should I stand up?
Yeah, sure. Stand up and.
Hello. I wanted to ask about the multiple drug resistance problem. We know, like in bacteria, that's a huge problem, but there were cases in viruses like for HCV or HIV that we experienced this. Then when we are treating with one type of drug, it turns to the pathogen turns to evolve to resist it. When we are trying to attack it in multiple ways with multiple drugs, it is stopped for many years and worked perfectly. It's why we haven't been able to do this to the multiple drug resistant bacteria.
That is a really excellent question. I think one of the strategy to be able to utilize antibiotic that we have right now is to use combination therapy. Taking lesson we learned from HIV and TB therapy. We learned very quickly with HIV, one drug doesn't work, two drugs doesn't work, three drugs. Yeah, you can hit the pathogen in multiple different mechanisms. Same thing with TB. So pathogen, particularly that are difficult to eradicate, that's very helpful. In antibiotics, obviously the issue has been that we don't want to overuse antibiotics because you're not just treating what's there. You're not just treating the HIV, yeah? You're treating the entire microbiome. So by giving many antibiotics a different drug class, yes, you can treat that particular infection, but the side effect is tremendous because you got the entire human microbiome in your gut. And so that's a challenging issue, but it hasn't been tested. Whether antibiotic combination, short course, hit hard, hit early, short, is still better than, but I really think the issue is beyond treating the patient that develop, secondary resistance. I think the issue, as I mentioned, is a global issue of environmental and agricultural use of inappropriate use of antimicrobial. Is more of an issue than patients.
I have a question about maybe one approach to antimicrobial resistance. And it just happens to be that a friend of mine was very involved in this work, Stephanie Stratby at UC San Diego, which is phage therapy, and in a sense bypassing the whole issue of the current classes of antibiotics and looking at phage.
Right.
I wonder if is anyone doing that?
So that's excellent. That's another very good strategy that we have to even go back. So phage therapy has been around for 100 years.
Yeah.
And people in the Eastern Europeans are still using it. In Russia, the people are still using that. So basically, these are viruses that target bacteria and kill them, but they're very specific for the bacteria. So the issue with phage is that you have to find the virus that target that particular strain of that particular bacteria. And so it's, it's a lot of work to keep virus, like the whole storage of it. But it's possible, and we've been using it now for particularly like very difficult to treat infection like mycobacteria when you run out of option, for example. So phage will probably be something we have to retreat to because it's using nature to kill nature, and it doesn't have resistant sort of mechanism. So I think that's an excellent point. There's people who work on it in the United States, and it's becoming more and more important because of exactly what you said, antimicrobial resistance.
Very commonly used in the research was taking place in the DoD.
Right.
And that's, I think, was tied to some of the cases where you had the resistant gram negatives that the phage therapy was used. One of the interesting uses of phage was actually as a diagnostic for anthrax, for Bacillus anthracis. The phage was used as an identification mechanism. That was another thing that came out of the Soviet Union.
Hi, Zhang Yang. I'm from Global Health Year 2 education. So my question would be a little bit broad. So like when we talk about a lot in the global health field, that we are shifting from the vertical program paradigm to an integrated paradigm. I mean, to tackle the future challenges. I mean, from your point of view, what would be the top priority for the international community to do? I mean, within this kind of new integrated paradigm. Method. Thank you.
Chris, you want to
I may have missed a little bit of the question. What is, just repeat it if you would.
Yeah, so there's a paradigm shift, right? From the previous vertical program to tackling the disease like HIV/AIDS. And then we are talking more about the integrated approach. So what would be the top priority? I mean, many people are talking about integrated approach, but what do you see? Will there be any top priority in your minds that we can do?
Now I've got at least what you were asking. I mean, the problems with siloed vertical systems are well understood in public health, and there are great examples of where you had influenza programs next to HIV programs, next to TB programs. I know our leader, Dr. Byers, is well familiar with the siloing of those issues. And there are reasons why that happened in the past, and we've been trying to break them down for many years. You need a solid infrastructure. The best thing we can do to combat whatever we spoke about as potential causes of pandemics is having a solid public health and medical infrastructure around the globe, whether in low and middle income countries, et cetera. You have to have that base. And when you have siloed programs, then it tends to make dramatic impacts for those particular issues. They are phenomenally successful, but you need to be leveraging them to have a broader impact. And that's where we are as PEPFAR changes from its HIV focus to a broader focus as well, and utilizes some of the systems that are in place. But we need that great infrastructure. That's where
Yeah, and I would just chime in on that, is that a major problem that we have is differences in being able to detect and surveil for whatever pathogen might be coming up. It's really sketchy and spotty across the world. So you have some more developed nations may have access to more diagnostic tools where they can identify things faster. But even in those countries, if they're not looking for it, they're not necessarily going to find it. So we really need just sort of a global effort to increase our diagnostic tools and to let people know what they could potentially be looking for, instead of just the standard set of things that they're always looking for. And then how do we, the infrastructure, how do we share that information more rapidly? Because that's what we're dealing with now, is things are rapidly evolving and emerging, and we need to get a handle quickly as these pandemics start to emerge.
Speaking of which,
diagnostics, I mean, diagnostics is kind of the poor stepchild that doesn't get enough credit. So we make diagnostics for potentially pandemic diseases. And we've come to the conclusion that we can make those prospectively before there's ever an outbreak. And we have kind of proven that. The problem is we are not virologists. We need people to work with. And we have done fungi, we have done bacteria, we have done viruses. So if whatever organism you have doesn't have a good point of care diagnostic, because point of care diagnostics are what really prevent pandemics, come talk to us. We are happy to work on just about anything.
That gets to the point about moving to the left, your epidemic curve. We're all familiar with your epidemic curves, right? What you want to do is shorten, and we heard all this during COVID. You want to limit the curve, and so the earlier you get a diagnostic, that a diagnostic is available to actually identify cases when they emerge, and you want to have some agnostic approach to that. Is it a virus? Is it a bacteria? That's really key. Is where on my side we've developed our diagnostics. That at least gets you started in the right direction, and the potential to identify new pathogens, which is actually where I thought you were going to land. Which is going to be
I told you.
I know you kind of pulled a curveball on me, but that was good.
So, I mean, I guess my one comment there is, oh, by the way, I agree with you completely, because our next R1 is the diagnostic for Nipah virus. So, but they have to be cheap, point of care. You kind of have to flood the market if you want to detect things early.
Let's take a question from you, and then we'll have a couple from the chat.
Okay, hi, Yisel, first year master's student in global health here. My question, I acknowledge the systemic issues. My question's more directed towards like the use of AI or machine learning to predict whether or not what the future, sequences could be that we will encounter or possibly can encounter. Is there like a group of people working on that here or like in the area?
I've been reading up here. Can you repeat that real quick?
No, it's okay.
Fielding these.
I'll start on that and then pass it on. And we've been picking, people have been looking at hot spots for where the next pandemics are going to occur, and they take into account all these variables we've been talking about for some time. Where have diseases emerged before, whether fungal, bacterial, or viral? Where is there the most anthropogenic change? Where are the human animal interactions changing most dramatically? Where is there the greatest urbanization taking place? And the movement, what happens, you get movement from people in rural areas to urban areas, and they go back and forth, and that actually creates a lot of opportunity for the emergence. And so that's all been modeled out. And so there's a few papers we can share that will show where those hot spots exist. Now, people are always trying to refine those hot spots, and that tells us where to look. And that's looking geographically, but then you also want to look at for emergence, which animal species. We talked about bats and the huge number of viruses they contain. Rodents were referred to earlier with plague, and you want to look there. Again, the non-human primates are our closest relatives and may be giving us the best clue as to what may be threatening us soonest. And so you can target different species, you can target different vectors, which we haven't talked about in this meeting. But there's a lot of energy going into identifying where to be surveilling for the next and up and coming viruses, but we need the tools to do
so. You can do spatial temporal modeling and looking at all kinds of different resolutions, but it's only as good as the data you have. Also, you can't put any variables in. And part of what we're doing in PIP is doing network analyses, looking at communications and networks between people. And then what their exposure are or is to environments and neighborhoods and things like that.
Bill Pan is doing a lot of work
Yeah.
with NASA and the NOAA groups too, so he's worth mentioning.
Yeah, absolutely. Thank you. We only have a couple minutes, so I want to give the opportunity for the Zoom chat. Rachel, do you want to maybe say one or two?
Yeah, I think a couple of these questions were already kind of covered. But one that I think is interesting, is Doug Short says we need to think beyond antimicrobials. What will the future of drugs look like? And so maybe we can think beyond the,
We've got a vote for Faj already.
Yeah. We try to answer that in 30 seconds. I want to get people in. Everything is rushed. I'm sorry.
Well, it's just
Or
somehow,
T-cells.
yeah, some of our best strategies come from microbes that already exist. Like we've mostly been borrowing things from what's actually natural products, right? These microbes have been sort of involved in warfare for centuries, and so we sort of moved to those natural products. There's been a lot of work that's done, like trying to evolve sort of chemical antagonists that can be used as drugs. I feel like we've largely been much less successful in using what's naturally evolved in the environment. So yeah, I think we are sort of at a, it's tough.
Yeah.
It's tough. It's not easy to develop drugs, and then for them to be clinically safe for use as well.
We got a couple upvotes from the QR code. So can you guys read that? So do the panelists agree, as Dr. Wood suggests, the actual looming threat is another influenza or coronavirus? Oh, quick answer on that one. That's a good one, if you can.
Influenza.
At least one off the panel.
Yeah.
Well, certainly the past is a good predictor of what you're likely to
Sure.
see. It's just that you can't ignore other threats, because we have been able to, somewhat successfully deal with these viral threats. So the question does become, what about an unknown threat that we've really never dealt with before, such as something that is transmitted in the air, much more in the spores in the air, for example, that are in our homes. You can't necessarily wear a mask constantly. So those are the kinds of things that we want to start to safeguard against.
What do you think? We have one more?
yeah, I think maybe
Okay.
the top one. 'cause
All right. Thank you for everyone who's voting. That's great. I love that. So last question, because we have to vote. We have a hard stop at 1 o'clock. What do the panelists think about the level of threat from potential bioweapons to applications of AI and biology? There seems to be a lack of policy and scientific safeguards in place. It's a good question.
There is a historical and ongoing overlap in the preparedness communities for both threats that are human derived as well as naturally occurring. So that people are aware of that. Safeguards are difficult to put in place entirely. What we don't want to, there's been a lot of concern between the scientific community and some of those who would seek to inhibit the distribution of knowledge, in that the concern being that it could have negative impacts through facilitating the creation of new bioweaponry, and that's a much longer discussion. There are things in place, but my point would be you'd have to be careful about restricting scientific communication.
The bioweapons are tricky because once you introduce things, even if it's targeted toward a certain population, it can quickly get out of control. So perhaps that's why we're not seeing the use of bioweapons en masse, as you might expect, that it could be used. But it's totally unpredictable and could end up targeting your own population. So maybe it's not the most effective bioweapon or to use bioweapons, period.
Just one positive example, the most recent outbreak, of course, was Mpox, monkeypox, which was a big issue last year. And the vaccine that we had was really developed, even though smallpox has been eradicated, in preparation for weaponization of smallpox. And it was stockpiled. We had to get it out of Denmark, but nevertheless, it's a highly effective, safe vaccine, and it was specifically developed because the old smallpox vaccines were just so immunogenic.
The creation of the Ebola virus.
Yeah.
vaccine as well.
Yeah, absolutely. And it was very striking that the epi of Mpox, when it broke out, was very specific to people under the age of smallpox immunization. And we didn't see Mpox in people who've been immunized for smallpox.
All right, I'm gonna call timeout and let Rachel take over.
Well, thank you again to all of our panelists and all of you for coming and everybody online. Just really quick at the end here, we're gonna do a hard 30-second closing statement from each of our panelists. And while we're doing that, we actually have this QR code where you can vote for what you think of these three might be the most likely to be our next unexpected pandemic. So I think the QR code works best, or you can text to one of these numbers to 22333. So with that, I think we'll go in opposite order, if that's okay, from when we start, and I'm gonna stop you like exactly at 30 seconds.
I'll just sit here and say that I think that the antimicrobial resistant pandemic is already here, is not coming. And that if we don't do something about it, we're gonna very soon move to a pre-antibiotic era where modern medicine is gonna be no longer modern medicine and we're gonna go backwards. So lots of work to be done. And I think that that's an area for young people to be aspire and go into to make a difference right now.
All right, and I'll just say that new fungal diseases are currently emerging. They're already rapidly on the rise. We're behind. We've never seen these really before. We're behind on diagnostics, surveillance, and treatment. We have few antifungal targets. We have no vaccines, and climate changes have really caught us off guard. We're all sort of struggling as a scientific community to really understand the impacts. So don't discount fungi, as they can spread from person to person, as well as spread through the air and spores that we breathe. And we're already starting to see scientific evidence that heat stress can actually stimulate the mutation rate in both plant infecting species and also human disease as well.
Hate to speak against AMR, but if people used antibiotics appropriately, it wouldn't be an issue. Fungi doesn't dead people. Comes down to diversity of viruses, facility for zoonotic spread, severity of disease, and lack of existing countermeasures make viruses thrive.
All right, so if you haven't already, go ahead and vote. We're gonna give you about 20 seconds.
We actually, we got a lot of responses and it has a setting that you have to pay for more. It filled up, so that's a good thing. I'm not sure what the limit is, but thank you all. If you don't want to be anonymous, we can also raise hands. It's a fun thing. It's not really a winner or a loser. I also want to acknowledge that it's not the presenters we're voting on, it's their case and the path, because they're all wonderful. All right, so on the poll, we have 20% for respiratory paramyxin viruses. If you want, you can show hands if you thought that was ideal. Okay, cool, great. And second place was Dr. Lay's worst case scenario with, I should say the percentages. So online it was 20%, 36% for this. If anybody wants to raise their hand for that, wow, good. Wow, okay, quite a few. And then via the poll, the most was 44% was Candida. Candida.